In the past few examples, we've tried to see how we can justify that a limit does not exist. And we might be wondering, how are we ever going to be able to show that a limit does exist? If you think about what happened back in example 2, you'll notice again that we checked actually at the start here infinitely many paths and had all of them come out to a value of 0. So if I wanted to prove that the limit was actually going to equal a specific value, then remember we had to say that the limit across all paths needed to actually come out to be the same value. However, that's not the same as saying if you check along infinitely many paths, you get the same answer all the time. So as I kind of state down here in this second note, in that above example, even though we checked infinitely many paths, that still doesn't tell us that the limit existed. So one thing that's kind of tough then to swallow at first is that in this class, we will never be able to justify that a limit exists by checking paths. That's just never going to be possible. There are too many paths to check, right? It's just never going to really work for us. So how do we actually show them that limits are going to exist? Well, what we're going to have to do is go to an extension of limit laws that we had back in a Calc 1 class. So here in this box on the next page, you'll see that I have some basic limits or limit laws that should feel fairly similar to some limit laws that you would have seen again back in Calc 1. So let's take a look and read at what we have here and try to identify the different rules going on. All right, so suppose that C is a constant, and suppose that this first limit here and this second limit actually exist. Okay, they don't come out as DNE, right? They actually exist. If that's the case, then these rules are fair game. If you're ever doing the limit of a function that's really kind of like an addition of two smaller things or a subtraction of two smaller things, you can break that apart and do the limit of each piece. Or you can always go in the opposite direction. If you had two things, two separate limits, you could add or subtract them together, turn them into one limit. Property number 2 down here technically has two rules. The first one here says if you're ever doing a limit and you have a constant multiplied by a function, you can always take the constant out and multiply it to the limit. So like do the limit of the function first, multiply by the constant later. If you're ever doing the limit of just a constant, you get just that constant. We've already kind of used that in some of the above examples as well. Here's a good one. Limit of two functions multiplied together is the same as multiplying those two individual limits. If you have the limit as xy approaches ab, but you're just doing it of x, then notice here it's kind of like the y and the b just don't even matter. You just have x approaching a, so your answer is a. And in a similar fashion, if you have the limit of just y, you would get a b out of that. Finally here on number 6, if you're doing the limit of a radical that has a function inside of it, you can kind of move that limit to the inside of the radical. And that is, you can do the limit of the inside part and then just apply the square root or the cube root or the fifth root after the fact. The only issue here is that we have to still make sure that the inside of the radical and the radical itself don't end up creating something that's nonsensical. So for example, if this was just a regular old square root, I'd have to make sure that my inside, the limit of that inside, doesn't turn into, say, like a -4, because then I won't be able to square root it without going into complex numbers. And remember, we're avoiding complex numbers in this class. Okay, so if I wanted to show that a limit exists, I would have to make arguments purely from what I know from Calc 1, from algebra, and from these extensions of these limit laws. Okay, so let's try to see some examples of this. Take a look here at this first one. Can I go ahead and see if this limit actually exists? Keep in mind that we're not just plugging in 0, 0 to see what happens. Okay, that's not what we're doing here. We have to go ahead and try to think about how I can make use of these laws in order to argue for this. Okay, well, one of the things that's immediately difficult here is that I have two things that are being divided, and I don't really have anything in my laws here that tell me what I can do with that. So what I'm going to focus on first is simplifying this algebraically. So I'll start by saying, note that x to the fourth minus y to the fourth over x squared plus y squared can be rewritten. I'm just focusing on the inside part. Notice that the top, I actually see here as a difference of squares. I think you could rewrite that as an x squared minus y squared and an x squared plus a y squared. And you might be able to then immediately recognize why that is super useful. Because once I have that, I can actually simplify out the x squared plus y squared and just be left with an x squared minus y squared. Okay? Well, once I have this, I can go ahead and immediately start to calculate the limit. So the limit as x comma y approaches 0, 0 is going to be, I should write my function down here first, but that's going to be equal to a limit of really just x squared minus y squared. Right? We can see that we've just replaced that function there. And if I want to go ahead and start applying some limit laws, notice that I could easily start to apply here, how about something like limit law number 1? I have two different functions that are being subtracted, so I can separate this out into doing a limit of each of those. So I'll do just a limit of x squared, and then minus a limit of the y squared. You can see how, again, annoying this is to have to write out my x, y approaching 0, 0 every time, but unfortunately, I have to write it. Without this, what you would put down would not be correct. Okay, so now I have this. How can I possibly deal with this? Okay, well, if I'm going to use the limit laws, I have to be careful here. Notice that I can't use anything like properties 4 and 5 yet, because I don't just have a limit of x, I have a limit of x to a power. But isn't x squared and y squared just the same as x times x and y times y? So that means I could actually use something like property number 3. I could actually go ahead and rewrite this as a limit as x comma y approaches 0, 0 of x, and then I could multiply that by another limit of x again, right? So I'm just using this property where I'm imagining this piece is x and this piece is also x. So I'm going to end up with a limit where I have x and I also have x. For the sake of space, though, notice that if I had two limits that are identical multiplied together, I could just say, and I'm going to square those. Okay. And then I can do the exact same thing for the y. I'm going to have x comma y approaching 0, 0 of just y, and that is all going to end up being squared. Of course, now I can go ahead and make use of properties these properties number 4 and 5. I have just the limit for x and just a limit of y, and so this is going to turn into 0 times 0, which is a limit of 0. So here I can absolutely confirm that I get a limit of 0. Okay, now notice that this kind of implies a couple things. First off, as I state in the note, if you tried to then show that the limit here didn't exist, let's say you were convinced that it didn't exist and you were going to try to prove it, you would be very unsuccessful because no matter what path you would try to take towards 0, 0, no matter what path, any path, the ugliest paths you can imagine, you would always end up with an answer of 0. So here, along every possible path, there is an answer of 0. Now, the other thing that would be kind of annoying, that is annoying here to note, is that like thinking through all of these limit laws and trying to like carefully write out all the fine details slowly step by step is kind of cumbersome. Like what happened in Calc 1, after you are familiar with these rules, it tends to be pretty common to start trying to apply multiple of them at the same time. And so let's take a look at how we would do something like that, maybe down here in example number 4. Okay, so here again I have another limit, and I want to show that this limit exists. So that means I'm not going to bother checking long paths. I'm going to think about limit laws, and I'm going to think about like Calc 1 limit techniques. Okay, one thing pops to mind for me immediately upon seeing this limit, and it pops to mind from what I recognize in Calc 1. So back in Calc 1, what would sometimes happen is you would have radicals, and then notice you'd have a number like outside of that radical either added or subtracted to it. And it could be really, really useful in cases like that to give a shot at multiplying by the conjugate. So I'm going to go ahead and attempt to do that here. So I'm going to say that my limit is x comma y approaches 0, 0 for x squared plus y squared divided by, I have my square root of x squared plus y squared plus 25. And then outside of that radical, I have minus 5. So I'm going to go ahead and I'm going to multiply by a fancy version of the number 1. And I'm going to do the square root of x squared plus y squared plus 25, but just with a plus 5 as opposed to a minus. Again, this might be reminiscent of things you did early on in a Calc 1 class. Now, the reason that we like to do this at times, or at least to give this a shot, is that this is going to force a difference of squares to occur in the denominator of the fraction. And the reason we like that is because that's going to simplify up very, very nicely. Notice here that I'm still going to get a limit with xy approaching 0, 0, but I can rewrite the denominator of my fraction now really easily. It's going to be the first term down there being squared, which is going to produce x squared plus y squared plus 25, and then minus the 5 being squared, which is going to also produce 25. Now, if you can't see that, just go ahead, put these two things in parentheses, and multiply them out like you would back in Algebra 1. But if you can see the difference of squares, you can immediately jump to the conclusion. Notice in the numerator, I'm going to get something really freaking ugly. So ugly, in fact, that I'm not even going to bother like doing any sort of distributing or anything. I'm just going to leave all of this kind of just as is, so I don't want to touch it. Now, you can see here, this is going to end up being really nice because the 25s are going to cancel. And once the 25s have canceled, then I can cancel my x squared plus my y squared. So this is going to leave me with a limit as xy approaches 0, 0. And I'm just going to have left this radical, x squared plus y squared plus 25. Let me shorten that up a little bit. And then I'm going to have my plus 5 at the back. So now I can start to think through my limit laws without actually carefully writing out each individual step. So for example, limit law number 6 that we had said that if you're ever doing the limit of a square root or any sort of a radical, you can kind of slide the limit and do the limit inside. Okay, so I'm going to imagine just doing the limit of the inside stuff. I'll square root the answer to that inside limit. Okay, the limit on that, well, actually, let me back up here really quick just to make sure that I'm recognizing. First, I'd really have to do the limit of both of these pieces, right? So I know I'm going to get the limit of the square root plus the limit of the 5. And the 5 is just going to give me a result of 5. It's a constant. Now I have to do the square root of the limit. That's going to be for the inside stuff. When I do that, that means I'm going to have to do a limit of the x squared, a limit of the y squared, and a limit of the 25. So I know what the limit of the 25 is going to be. That's just going to be 25. I now can do the limit of the y squared. That's kind of like what we saw up above. That's going to be the limit of y times the limit of the y. So this is really just going to be 0 squared at the end of the day. And over here, I'm also going to get 0 squared. So now I can go ahead and simply see here that this is going to be the square root of 25 plus 5, which is going to be equal to 10. So the limit is 10, right? Notice I did a lot of those steps in my head, but notice what I was not doing, because a lot of people make this confusion. A lot of people are going, oh, Kyle, what you did is you just plugged in 0. No, I did not plug in 0. That looks like what I did, but that is not what I did. And if that's what you think you're doing, you will get in trouble on occasion with limits. I was thinking through the limit laws. I was using limit law number 6, number 3, number 4. I was using number 5. I even used this second half of number 2. But I was thinking specifically about those limit laws. Plugging in 0, 0 is not the same thing as taking a limit. At least, it's not the same all the time. In the videos to come, we'll take a look here at kind of when it is the same thing to just attempt to plug in 0, 0. That can be done, but there are very special circumstances that have to be met in order to make that possible.